Hey everybody, welcome to our last lecture in Real Analysis 2. I will conclude with some proofs and some statements of theorems that you should see and things that you will need for the final exam. The first thing that we're going to look at are properties of definite integrals. Now, in the previous lecture, we saw some properties of indefinite integrals or antiderivatives. And property 1 and property 2 may look familiar. And that's because there are analogous properties with indefinite integrals. You've seen these before. The only difference between these two and the analogous properties that we saw with indefinite integrals is that the properties that we saw with indefinite integrals or antiderivatives, the integrals had no limits, no upper and lower limits. But other than that, the properties were the same. And so we're going to mention that these are true because the analogous properties of antiderivatives are true. And just think about it. How do we compute a definite integral? Well, let's see. We haven't talked about that, have we? We haven't talked about the fundamental theorem of calculus, which says that if we want to compute a definite integral, that we compute the antiderivative of the function and then just plug in the upper and lower limits and subtract one from the other. So essentially, when we're computing a definite integral, we're computing an antiderivative and then just evaluating it at the upper and lower limits. So because the analogous properties for antiderivatives hold, these same properties hold for definite integrals as well. Now for properties 3, 4, and 5, there are no analogous properties for antiderivatives. Notice here the upper and lower limits of integration are the same. And this integral is going to be 0. If the upper and lower limits of the integral are equal, then the value of the integral is 0. We will not prove this today. This will be one of our final exam exercises. Now, property number 4. What happens if we take a definite integral from a to b and we switch the limits? The upper limit becomes the lower limit. The lower limit becomes the upper limit. Property number 4 tells us that if we do that, we get the negative of the original integral. We're not going to prove that today. That's one of our final exam exercises. And that final exam will be coming out within the next 24 hours. And then our final property for definite integrals. Notice that c can be any real number. And the upper limit of the first integral is the same as the lower limit of the second integral. And when that turns out to be true, this property tells us that essentially we can squeeze this integral together and get a single integral whose lower limit is the lower limit of the first integral, and whose upper limit is the upper limit of the second integral. And I will mention C C does not have to be between A and B. C can be outside this interval. We will not prove this exercise today. This is another one of our final exam exercises. I'll give you a couple of appropriate hints for these, but we will not prove these today. These will be on the final exam, and you get to prove them for yourselves. So these are, and maybe I should say parenthetically, algebraic properties of definite integrals. Yeah, let me just lower this a little bit. Now, of course, the assumption here is that f is integrable. I haven't stated that as a hypothesis, but of course that has to be part of the hypothesis. Otherwise, this thing doesn't exist. So if the value of x is bounded below and bounded above, then the lower bound times the length of the interval is less than the integral of f of x. The upper bound of the integral times the length of, the upper bound of f of x times the length of the interval is greater than the integral of f of x. Before we prove this, and yes, we will prove this, we will prove some things today. This is one of them we'll prove. And it would be a good idea to study these proofs before you begin working on the final exam. Study the proofs and take some notes, just as if you were in class in person. Do that. Study the notes before you do the final. We'll give a graphic demonstration of this. Before we prove it. Okay, let's see what this looks like. Here's our graph, y equals f of x. And I apologize for not writing larger, I really should. Here's m. Here's capital M. This line is the line y equals capital M. This line is the line y equals little m. And we'll have this be our interval a to b. And I guess to demonstrate this graphically, I'm tempted to superimpose these things one on top of the other, but I think that will be too much to take in with the eyes. So here's what I'm going to do. Now, how do I know that this area is m times b minus a? Well, the area of this region is just a rectangle of height m and of length b minus a. Now, let's look at our definite integral. Here's y equals f of x, and here's little m. Here's big M. And here's our function, y equals f of x. And if f is non-negative, the integral of f, the definite integral of f, is just the area bounded by the graph of f of x and the x-axis. So that area is just the integral. And I sure would like to fit that other thing in. Please accommodate me. Here's capital M. Here's A. And here's B. Let's see, can we see that? No, here's B. Maybe we can see that. And this is y equals capital M. I didn't want to do that. Okay. Notice that the area of the definite integral is definitely greater than the area of this rectangle, which is just little m times b minus a. And the area of this big rectangle is capital M times b minus a, because the height of this rectangle is capital M. And the length of this rectangle is just b minus a. So capital M times b minus a is the area of this big rectangle. And clearly the area of this big rectangle is greater than this area, which is the integral from a to b of f of x dx. So that's sort of a picture proof of this theorem. But we're going to do a hardcore analysis proof of this statement as well. So in each interval, we select a point at random, call it psi sub I. And what are we going to do? Clearly, we're going to construct a Riemann sum. But before we do, we'll make this observation. Whoops. And let me make it correctly. See, I did say that I wanted to make this correctly, didn't I? Okay. Let me try it again. Okay, that's what I really mean. Psi sub I is an x value in this interval. So f evaluated at psi sub I is greater than little m, because little m is less than or equal to f of x for all x in the interval. And f of psi sub I is less than or equal to capital M, because capital M is greater than or equal to f of x for all values of x in the interval from a to b. So now we make our Riemann sum. There's one thing I have to correct here. This upper limit is n as in Nancy, not m as in Margaret. There we go. This thing, xi minus x sub I minus 1, is the same in each expression. So essentially, I've taken each of these sides of the inequality, m, f sub psi sub I, capital M, and I've multiplied all three sides of this inequality by x sub I minus x sub I minus 1. And then I just let I go from 1 to n. So our inequality holds. And I guess what we should do now is recognize what this thing is. This is delta x sub I. And this is delta x sub I. And this thing is delta x sub I. And you know what? If a function is integrable, which we assumed in our hypothesis, that means that when we compute the limit of the Riemann sum to get the definite integral, we get the same definite integral regardless of our choice of partition, which means that what we could do is just make things easy for ourselves and assume that we've chosen a very simple partition where we take the interval from A to B and we just divide it into n subintervals of equal length. Now, we don't have to do this. What the heck. But we can do this. And we can just say, okay, this is delta x. If f is integrable, this works for any partition. I'm going to take the lazy man's way out. And I'm going to put what this really is down here. I'm just going to say delta x. Now, why did I do that? I'm just going to make things easy for myself and say delta x is b minus a over n. I've divided the interval from A to B into n subintervals of equal length. And now I'm going to take this inequality and I'm going to take the limit of all sides of the inequality as delta x goes to 0. And I will note parenthetically, I don't have to write this down, but I will note parenthetically that as the width of each rectangle gets smaller, then that means that we have more rectangles in the interval from A to B. If the rectangles get thinner, then we have to have more rectangles. So as delta x goes to 0, the number of the rectangles goes to infinity. Now, I don't have to write this down, but I'm doing it just so that we understand what's going on. we'll remind ourselves of what a definite integral is. So here's our f of x here. It's just the constant, little m. And the fundamental theorem says when we compute the limit as delta x goes to 0, the summation sign becomes an integral sign. The x sub I becomes an x. The delta x becomes dx. And the upper and lower limits of our integral sign are the endpoints of the interval that we partitioned into subintervals. So this thing is going to become the integral of f of x dx. Here's our f of x here, or our f of x sub I. So this will be the integral of f of x, which in this case is capital M, Now, let me mention something in hindsight. The points that I picked at random in each subinterval, I called them psi sub I. Could I have called them x sub I? Yes, absolutely. So in hindsight, just to avoid confusion, it would have been better if I had just called this x sub I instead of psi sub I. Now, the fundamental theorem of calculus, let's see. What am I trying to prove here? Yes. The fundamental theorem of calculus which we actually have not proved yet. We'll assume that we have this in evidence. How do we compute a definite integral? Compute the antiderivative of the function. Plug in the upper limit, plug in the lower limit, and subtract. So let's see what we got here. The antiderivative of this thing is little m times x, evaluated from x equal a to x equal b. I'm going to keep this exactly the same. And the antiderivative of this thing is capital MX, evaluated from x equal a to x equal b. So let's see, how do I prove this? Or how do I evaluate this? I plug in the upper limit, I plug in the lower limit and subtract. And the same thing here. I plug in the upper limit, I plug in the lower limit, and I subtract. Oh, that's what we wanted to prove in the first place. Okay. So that's actually what we proved. Now, why do we care about this thing? I guess the answer would be that in analysis, we may be working with a function that we don't really know how to integrate. And what we'd like to do is maybe approximate it as closely as possible for theoretical purposes. And maybe the way that we can do this is just to get a lower bound on the value of the integral and an upper bound on the value of the integral. This is mainly for theoretical purposes. But if we continue in analysis, this will be one of the tools in our toolbox. In the previous proof, I used a theorem that we hadn't proved, the fundamental theorem of calculus. And one of the reasons I didn't prove it is because that's going to be one of the exercises on the final exam. So that's why we hadn't proved it. But technically, I should have at least stated the theorem before I used it. So let me do that now just so that I don't do that same misstep again. Okay, notice that capital F is a function of the upper limit of this integral. The upper limit of this integral is x, and capital F is a function of that variable. So we're computing the derivative with respect to the upper limit of this integral. And the fundamental theorem of calculus says that this turns out to be the integrand, f of t, evaluated at the upper limit. And as a matter of fact, we can restate it as such. We have an integral from a to x of f of t dt. We're computing the derivative with respect to the upper limit. And the fundamental theorem of calculus says that this is going to be the integrand f of t evaluated at the upper limit x. That's the fundamental theorem of calculus part 1. And essentially we break it into two parts just to make each one easy to get a handle on. And the fundamental theorem of calculus part 1 is something that we actually use to compute the rest of the theorem, the fundamental theorem of calculus part 2. So let me state that. So if capital F of x is any antiderivative of little f of x, then the definite integral of f of x definite integral of little f of x dx from x equal a to x equal b is the antiderivative capital F evaluated at the upper limit minus the antiderivative capital F evaluated at the lower limit. And remember from calculus, when we evaluate a definite integral, and for some reason or other, when we evaluate a definite integral and we compute the antiderivative capital F of x, we never add the plus c. And one explanation for that is that the fundamental theorem of calculus tells us that any antiderivative capital F of x will do. So why not make it simple as possible, and just choose the antiderivative capital F of x that has 0 as a constant term. The plus c in our antiderivative is going to be 0, since we can choose any antiderivative. Why not choose the antiderivative capital F of x that has 0 as a constant term? Now there are other explanations as to why we don't add the plus c when we're doing a definite integral, but this is a pretty good one, I think. Capital F of x can be any antiderivative, so why not just make it simple and choose the antiderivative that doesn't have a plus c. No constant term. Okay. Fundamental Theorem of Calculus 1. Fundamental Theorem of Calculus Part 2. We use the first to prove the second, but we're not going to do that today because these are two of your final exam exercises. And am I the heartless stinker that I am appearing to be right now? Hopefully not. I intend to give you copious hints on how to work through these two, just to be fair about it. But these will be final exam exercises, so we will not prove them here. I did state them here because in the previous proof I actually appealed to the Fundamental Theorem of Calculus, Part 2, when I evaluated the integrals, and then I thought, what a moron. I haven't even stated the Fundamental Theorem of Calculus yet. So that was a misstep on my part. I'm not saying necessarily that I should have proved this before I did the previous exercise, but I should have at least stated the result. I'm doing that now just so that I don't make the same misstep again. And we do have one or two more things to prove before I end the lecture and go back home and crank out the final exam to send to you. I wasn't planning on doing this, but I think maybe I'll illustrate this graphically as well. Before we prove something, we should have, well, I won't say we should have, but before we prove something, it's nice if it's possible for us to see intuitively why something is true. So let's just look at this graphically and see why this would be the case. So here is y equals f of x. And here is our friend y equals, let me write that larger. Our very dear friend y equals g of x. And notice that since the graph of g of x lies above the graph of f of x, g of x must be greater than f of x, greater than or equal to f of x. And now we'll just draw these things separately and see the common sense behind our theorem. Here's y equals f of x. And here's A, here's B. And the bounded area is the integral from f of x, the integral from a to b of f of x dx. Now let's do the same thing. I think that's about as close as I'm going to come to reproducing g of x. Here's A, and here's B. And the area bounded by this graph and the x-axis is the integral from a to b of g of x. And we look at the two regions and we say, hey, this one's bigger than that one. And so, of course, now we understand, okay, this integral, g of x, is bigger than that integral, f of x. So that's essentially the common sense behind the theorem that we're about to prove. But we want to do it analytically, and actually going through this proof and studying this proof will probably be helpful before we embark on our final exam. So this proof and the one that came before it are good proofs to study. They really are. They're good proofs to study and good proofs to work through ourselves with pencil and paper. Okay, our hypotheses are given, namely that f and g are integrable, so these integrals exist, and throughout the interval ab, f of x is less than or equal to g of x. I'll let delta x be b minus a over n. Okay. Let x of I be any x value Now I'm beginning to see why I used psi sub I in the previous proof, but this is okay. Tell you what. There we go. X sub I is A plus I delta X. So that means X sub naught equals A plus 0 times delta X, which equals A. X sub 1 equals A plus 1 times delta X. X sub 2 equals A plus 2 times delta X. X sub n equals A plus n delta X. But let's see, what is delta X? Isn't delta X B minus A over N? Yeah, that's what it is. Oh, and look, these two things cancel out. And I have A plus B minus A. Oh, that's just B. Okay, so that works out the way it's supposed to. Good, I like that. And I guess to my chagrin, I'm going to have to go back to using psi sub I. Oh well. So we'll pick psi sub I to be any point in the ith subinterval. In each case, f evaluated at psi sub I is going to be less than g evaluated at psi sub I because of our hypothesis. Our hypothesis is that g of x is greater than or equal to f of x for all x in the interval ab. So what I'm going to do now is prepare to construct my Riemann sums. I'll multiply both sides here by delta x. And we're just taking this inequality and multiplying both sides by the same positive number. So the inequality stays the same. So when we add all of these things up, the inequality is preserved. And you know what? I messed up. I forgot my delta x's, and they're very important. That's better. We have an inequality. Now we're going to compute the limit as delta x goes to 0. And the inequality will still be preserved. And note again, even though we don't have to write this down, that if delta x goes to 0, that also means that n is going to infinity. And what is this going to be? Son of a gun. The summation sign becomes an integral sign, and the psi sub I becomes an x sub I, or just an x, and the delta x becomes dx, and the limits of the integral are always the endpoints of the interval that we partitioned into subintervals. Those endpoints were a and b. The same thing happens here. The summation sign becomes an integral sign. The psi sub I becomes our x. The delta x becomes dx. And the upper and lower limits are the endpoints of the interval that we partitioned into subintervals, a and b. And this was exactly what we were supposed to prove. So we are done. Excellent, excellent. Maybe just one more theorem. Oops. If we compute the absolute value of an integral, that's going to be less than or equal to the integral of the absolute value. And I should probably just go ahead and prove this, but I can't resist the urge to show this graphically. And I'll use a specific example this time. A is 0, B is 2 pi, and f of x equals sine of x. Now, the integral from a to b of f of x dx, in this case, is the integral from 0 to 2 pi of sine of x. And to evaluate this, we compute the antiderivative, cosine of x, and then we plug the upper limit into the antiderivative, and we plug the lower limit into the antiderivative. And let's see, cosine of 0, that's 1. Cosine of 2 pi, that's 1 also. So this turns out to be a big fat 0. Now suppose we do the integral a to b of the absolute value of f of x. So that's 0 to 2 pi, absolute value of sine of x, dx. And let's see, what's the absolute value of sine of x? Well, that depends. From x equal 0 to x equal pi, the sine of x is positive, so absolute value of sine of x is just sine of x itself. So from 0 to pi, absolute value of sine of x is just sine of x. But from x equal pi to 2 pi, sine of x is negative. So the absolute value of sine of x between pi and 2 pi is negative sine of x. And if I integrate this, I get what? Negative cosine from x equals 0 to x equal pi. And here I get positive cosine from x equal pi to x equal 2 pi. And so I get negative cosine of pi minus a negative cosine of 0 plus cosine of 2 pi minus cosine of pi well, let's see. Cosine of pi is 0. No, it's not. Cosine of pi is -1, but negative that is +1. Cosine of 0 is 1. So minus a -1 is +1. And cosine of 2 pi is 1. And cosine of pi is -1, but we're subtracting that, so that's +1. We get 4. Son of a gun. The integral from 0 to 2 pi of absolute value of sine of x dx is 4. And that is certainly greater than what we got up here, which was just, well, let's see. The integral of sine of x. What happens if we compute the what happens if we take the absolute value of this thing now? Absolute value of the integral from 0 to 2 pi of sine of x dx is equal to the absolute value of 0. Yeah, so the integral of the absolute value is definitely greater than or equal to the absolute value of the integral. So in this case, it holds. But maybe the best thing that we can do is to go back and look at this graphically. Let's go back and look at this graphically. Same example. Oh, I'm not doing this justice. Okay, that looks a little bit better. The area is positive. Here the area is negative. And actually the geometric area, the area in a positive sense of each region is the same. But if we integrate this, we're going to get negative area. Numerically, they'll be exactly the same, except one's positive, one's negative. And when we add them together, we get 0. So how should I say this? We add those two things together, we get 0. So the integral of, the absolute value of the integral of sine of x is the absolute value of 0, which is 0. Oh, no, let's now look at the absolute value of sine of x. Let's say y equals absolute value of sine of x. And wherever sine of x is negative, we're going to do the absolute value of that and make it positive. So this is what the absolute value of sine of x looks like. And in each case, the area is positive. And so in this case, when we integrate from 0 to 2 pi, the sine of x, we have a positive area here, a positive area there. We add them together, and we get 4. The area of each one of these regions is 2. We add them together, we get 4. So essentially, this is a graphic illustration of why the integral of the absolute value of a function is greater than or equal to the absolute value of the integral of the function. Now, when would these things be equal? Essentially, they'd be equal exactly when f of x doesn't change sign on the interval. If f of x is negative throughout the integral and we do the absolute value, we get something positive. If f of x is positive on the entire interval and we do the absolute value, we get something positive. If f of x changes sign, then the region in which f of x is negative will cancel out some or all of the region in which f of x is positive, area-wise. So if these two things are equal, then essentially f of x doesn't change sign throughout the interval. That's a little white lie, but until we have measure theory, that explanation will have to do. Yeah, if f of x does not change sign in the interval, then these two things are going to be equal. Okay, all partitions yield the same integral. So what the heck? We'll just partition the interval into n subintervals of equal length. And we'll make it easy on ourselves. Let's see, maybe I can stick something up here. X of I equals A plus I delta X. Did we fit that in? I think so. So that's the usual partition. All the subintervals are the same length. And in each interval, we'll pick a point at random and call it psi sub I. Let's see, why is this true? Well, before I say why it's true, I'll add another side to this inequality. And I am going to add a disclaimer up here to my hypothesis. We are assuming that this is an integral in the typical sense where the lower limit is less than the upper limit. I need to assume that, though. And you know what? I think I'll put this less than or equal sign right over here. In each of these terms, we have the absolute value of a product. So what I can do is I can turn this into the product of the two absolute values. And you know what? I think I will justify the first part of this right now. Why is this thing less than or equal to that thing? If you said the triangle inequality, you're right. And I think I'm going to continue this, not down below here, but up above. In each of these terms, I can write this as f of psi sub whatever times delta times the absolute value of f of x. And the reason for that is that the absolute value of a product equals the product of the absolute values and let me make a slight correction here. If the absolute value of a product is equal to the product of the absolute values, when I go from here to here, writing the absolute value of each product as the product of the absolute values, since each of these things is equal to each of these things, should I really have this here, or should this be an equal sign? If you were concerned about this when you saw me write that, you were right to be concerned. And now I'm going to do one more thing. That we assumed that B was greater than A. So that means that B minus A over N is going to be a positive value. So I don't really need the absolute value of delta x here. Now, let me just restate what I established here. I started with this thing, and I ended up with this thing. Now, what is that? I'll rewrite this. F psi 1 delta x plus f psi 2 delta x f psi n delta x absolute value is less than or equal to this thing that we ended up with. Absolute value of f of psi 1 delta x, absolute value of f of psi 2 delta x, plus dot 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 absolute value of f of psi sub n delta x. That's what we established. And we have essentially the absolute value of the sum of these things less than or equal to the sum of all of these terms. What should I do here? Well, I think what I'm going to do is just compute the limit of each thing. And note that while delta x is going to 0, it's also the case that n, the number of subintervals and the number of rectangles, is going to infinity. I don't have to write that, but I'm just reminding ourselves of what happens, what's actually happening here. let's see, what happens as delta x goes to 0 here? This thing turns into an integral. So we get the absolute value of the integral. The summation sign turns into an integral sign. The psi sub I will turn into x. The delta x will turn into dx. And the limits on the integral sign are the endpoints of the interval that we partitioned into subintervals. And the same thing happens over here. The summation sign turns into an integral sign. And our function, absolute value of f of psi sub I, turns into absolute value of f of x. Delta x turns into dx. And the limits of our integral are the endpoints of the interval that we partitioned into subintervals. And there we have it. And again, this is mainly for theoretical purposes. This is a tool that we may use in analysis if we continue to do analysis after this course, and I have a feeling a number of you will. This is just a tool that we want to have at our disposal when we do analysis. Now, everybody, this does conclude our last lecture. I think we were all hoping that by now we could be back in the classroom and seeing each other face to face, and that's not going to happen. Those of you who are going to be around next year, I am looking forward to seeing each and every one of you. Those of you that are graduating, I guess it's my understanding that the university is still planning to have graduation exercises at the end of July, not just for those graduating in the summer, but also for those graduating in the spring. And so if you are graduating this spring or this summer, and you're going to be at the ceremonies, I will delight to see all of you. You've been a wonderful bunch of kids. Forgive me for calling you kids. I know you're adults, but I'm an adult, but I'm not a young adult by any stretch of the imagination. So when I look at you as kids. And you're a wonderful bunch, you are. Each and every one of you, without exception. And I certainly do hope that I get to see all of you again. And not just once, although if it's graduation and that's when I see you, that's fine. But I am really looking forward to seeing from you and hearing from you in the future. By the way, one of our graduates from last summer, Narajan Korella, has been emailing me regularly, and he's a nice fella, he definitely is. And he keeps asking about all of you and how you are doing, and asking about the faculty and the department. He's up at Villanova right now. Same situation there. The university is pretty much shut down. But he's asked on a number of occasions about the faculty and about his former classmates here, just very concerned about all of us. And he's been nice enough to keep in touch with me since he graduated, and I appreciate that. And hopefully we can do that too. Hopefully we will see each other at least once, if not more, in the future. I'm looking forward to that for sure. But you've been a wonderful bunch of kids. Forgive me for calling you kids, but you're a wonderful bunch. each and every one of you, and it's been my pleasure to have you in the class.